Good morning to all of you. Today we are studying about dye. Introduction. A dye is a colored substance which, when applied to a fiber, impact to it a permanent color. The color imparted is resistance to the action of light, water, and soap. Some important characteristics of dye are: first, it should impart a suitable color. Second, it should be resistant to action of water, soap, detergent. Third, it should be capable of fixing itself to the material to be dyed. Fourth, it should be fast to sunlight, heat, and other normal atmospheric conditions. Fifth, it should be perfectly soluble in water. It may be noted that all dyes are colored, but all colored substances may not be acted as dye. Essential of colored substance to act as dye. Some essentials of dye are: first, presence of chromopores. They are the group which produce color to a dye since they are capable of absorbing light in the near ultraviolet region. NO2, carbonyl group, etc. are some of the chromopores. The compound in which chromopores are present are called chromogens. Second, presence of oxochrome. A dye should be resistant to the action of light, soap, water. Clearly, it should attach to a fiber by means of suitable chemical bond. The group which form suitable chemical bond are either acidic or basic in nature. Such group are called oxochrome or colored enhanced group. OH, sulfonic group, sulfonic acid group, amide group, etc. are some of the oxochromes. A chromogen without any oxochrome can never act as the dye. Color and constitutions. A. Color. We know that when white light falls on a substance, three processions may occur. First, in case of light is totally reflected, the substance appears white. In case the light is totally absorbed, the substance appears black. Third, in case the light is partially absorbed and the rest is reflected, then substance has the color of a reflected light. Wavelength, color absorbed, color reflected. When any substance absorbs violet color, it gives yellow green color. When a fiber absorbs blue color, it gives yellow color, and so on. Also, if only a single band is absorbed, then the substance has a complement color of the absorbed band. For example, if substance absorbs blue color, then reflected light will be yellow color. The reason is that yellow is a complementary color of blue. In fact, no substance absorbs a single band. No dye has a pure shade. For example, magenta green predominantly reflected green light, but also to small extent it also reflected red, blue, violet colors. It may however be noted that substances which appear to be colorless also have absorption spectra. In such cases, absorption takes place in IR and UV region but not in the visible region of electromagnetic spectra. B. Relations between color and constitution. Many theories have been put forward from time to time to related color with the molecular structure of a compound. A few such theories are described below. First, Witt's chromopores oxochrome theory. O. Witts put forward his theory regarding color and constitution. It is known as chromopores oxochrome theory. The main point of this theory are as follows. First, a compound should essentially contain certain groups which are called color enhancing group or chromopores. These groups generally contain double or triple bond. More the number of such groups in compound, deeper in the color. Some important chromopores are nitro, nitroso, azo, carbonyl, thiocarbonyl, ethylene, etc. Second, the compound which contain a chromopore is called chromogen. Niro group usually impact yellow color to the substance. In CH double bond CH compound, intensity of color increase if the number of double bond in conjugation increase. Third, there are certain groups which when present along with the chromopores deepen in the color. Such groups are called oxochrome. The oxochrome do not produce any color in the absence of a chromopores. Oxochrome are essential group for the chromogen to act as dye. Some important oxochrome are OH, OR, NH2, NHR, etc. In C6H5, CH double bond CH and C6H5, as the number of conjugate diene increases, the color deepens. For example, C6H5CH double bond CH2 twice C6H5 is colorless, whereas C6H5CH double bond CH thrice C6H5 pale yellow color. Beta carotene pigment present in carrots has orange red color dye due to the presence of 11 conjugate dye double bonds in it. Also consider the following compound containing chromophores. Let us consider the following dye. OH is the chromophores is color in deep orange. Second, in this dye NH2 is oxochrome, color is red yellow. Third, secondary amine is oxochrome, color is deepen red. Bathochromic effect. This effect is due to a group which, when introduced in a chromosome, shift the absorption to the high wavelength. Thus, this group causes a red shift, such that absorption shifts toward the red end. Such groups are oxochrome, which help in the deepening of a color. Hypsochromic effect. It is an effect by virtue of which the absorption is shifted toward shorter wavelength. The absorption should shift toward shorter wavelength is called blue shift. Valence band theory. According to the modern concept, valence band theory explains fully the effect of a group in the absorption of color. The electron pair of a molecule in its ground state are in the state of oscillations. When a molecule is placed in a beam of light, it absorbs photon of light. The molecule gets excited. The electron absorbed in is clearly the difference in energy between the two states of the molecule. Smaller the difference in energy, longer is the wavelength absorbed. It may be noted that the maximum energy is required to excite sigma electron, lesser energy for the pi electron, and still lesser energy is required to promote delocalized pi electron. Clearly, the absorption in wavelength is raised if first there is a greater conjugation in double bonds. Second, there is a greater delocalization of pi electrons. We know that ethylene is colorless, but polyene is colored. Actually, the intensity in the color increase with increase in number of double bond in a conjugation. For example, ethylene, one double bond absorption at 170 micrometer, while butadiene absorbed 217 micrometer. The bathochromic shift to longer wavelength is more pronounced if double bonds are in conjugation as compared to isolated double bond in which there is a little interaction between them. In a compound of highly conjugated system, the p orbital of carbon atom overlap and cause extensive delocalization of pi electrons. The net result is that the energy level of a highest occupied orbital is raised and that of the lowest unoccupied anti-bonding orbital is lowered. Now this absorption corresponding to the transition of a lower energy or higher wavelength. As the extension of a conjugation increase, the energy level of highest occupied molecular orbital is raised while the energy level of lowest unoccupied molecular orbital is lowered. Due to this decrease in energy absorption, the wavelength is raised. The absorption maximum is usually shifted 15 to 45 micrometer toward higher wavelength in conjugation system as the electron density is spread on 4 carbon atoms. A highly conjugated system such as beta carotene absorbs longer wavelengths which fall in the range of the visible spectra. Beta carotene is a highly conjugated system and it appears orange. As already stated, which the increase in conjugation, the energy level of excited state is lower and that of the ground state is raised. The decrease in energy shifts the absorption to high wavelength. The presence of oxochrome with plus I plus R or minus I minus R effect extended the conjugation system and thus shift the absorption to the higher wavelength. Third, molecular orbital theory. According to this theory, when a substance absorbs a photon of light, one electron is promoted from a bonding or non-bonding orbital to an anti-bonding orbital, depending upon the type of electron present in a molecule. Different type of electron transition are possible. First, anti-bonding orbital, which is associated with the excitation of a sigma bond. Sigma electron is called sigma star anti-bonding orbital. So sigma to sigma star transition takes place when sigma electron is promoted to anti-bonding sigma star orbital. It is represented as sigma to sigma star transition. Second, when a non-bonding electron gets promoted to anti-bonding sigma orbital, then it represents as n to sigma star transition. Similarly, pi to pi star transition represent the promotion of pi electron to anti-bonding pi orbital, such that pi star orbital. Similarly, when n electron is promoted to an anti-bonding pi orbital, it represents n to pi star orbital. The energy required for various transitions obey the following order: maximum energy sigma to sigma star, then n to sigma star, then pi to pi star, then n to pi star. It may be noted that pi to pi star and n to pi star transition lie in the ordinary ultraviolet region. As the conjugation increase absorption due to pi to pi star transition shift to longer wavelength and may reach visible region, which is responsible for the color. When ethylene molecule get excited, it gives CH2 diradical. The electron cloud is spread on two carbon atoms and absorption occur at 170 nanometer. Butadiene has two double bond in conjugation. The conjugation shift absorption to longer wavelength and it absorbs at 212 nanometer. The bathochromic shift is explained as below. A double bond consists of two pi molecular orbitals such that one bonding and one anti-bonding. But when two double bonds are in conjugation for MO molecular orbital result, two of these are pi 1 and pi 2 and each occupy a pair of electrons. The other two are anti-bonding molecular orbital. As a result of increase in conjugation, the energy of higher occupied molecular orbital pi 2 increase and that of the lower unoccupied molecular orbital decrease. Clearly, pi 2 to pi 3 star transition occur at lower energy or higher wavelength. Also, as the two molecular orbitals come closer, the interaction between them increase and due to this absorption is intense, such that T maximum increase. Similarly, a molecule with three double bonds in conjugation absorb at still higher wavelength. It is found that a compound with more than 6 double bonds in conjugation start absorbing in blue region and the absorb appear yellow, which is complementary color. Beta cartesian absorb in the greenish blue region. Now let us consider benzene and polynucleic aromatic compound. Benzene absorb at 252 nanometer due to pi to pi star transition. Naphthalene and anthracene with increased conjugation absorption at 2 to 25 nanometer and 375 nanometer respectively, but still they are colorless compound. Naphthalene is yellow at 474 nanometer and penthacene is blue at 580 nanometer. Classification of dye. Dye can be classified in the following way. First, mordant dye and chemistry of dyeing. These dyes require a mordant for dyeing animal or a vegetable fiber. For an acidic dye, a basic mordant is used and vice versa. For acidic dye, the mordant or metallic hydroxide, while the basic dye tannic acid is generally used. For metal mordating, the fiber is dipping into a color of metallic salt and the faded fiber is then dipped into the solution of dye. This procedure is an insoluble colored lake which is fast to washing. For tanning, mordanting, the fiber is dipped into a tanning bath, but since the lake are dull and tend to the frigative, tartramatic is added to the tanning bath. This produces brighter and more insoluble lakes. The color of lake depend on the metals such as iron, chromium, aluminium, etc. Lakes are chelated compound formed between the metal and the dye. The majority of the component dye owes their special property to the presence of hydroxyl group, and it appears that dye containing one hydroxyl group while be more dominant mordant if their hydroxyl group is ortho to a carbonyl, nitro or azo group. These dyes are primarily used to dye wools. The cloth is first dipped in a solution of a suitable metal salt and the soaked fiber is then dipped in a solution of dye. Insoluble color complexes are formed on the fiber. Metal ion first attack to the fiber and dye molecules then link to the metal ion by covalent coordinate bond. For example, seeing the metallic of aluminium ion and aligerine. Al3 positive ion form blue color, Cr3 positive ion forming brownish red and magnesium form violet color. Second, wet dye and chemistry involved. These are insoluble in water but are reduced by sodium hyposulfate to alkyl soluble compound which are readily reoxidized to the dye. This reduction compound are often white or colorless and so are called leuco compound. Dyes in the leuco condition dye both animal and vegetable fiber directly. Wet dye are mostly used on cotton. The fabric to the dye is soaked in the alkaline solution and then oxidized to the insoluble colored form by exposure to air or by some oxidizing agent such as preboric acid. As important example of wet dye in indigo. Third, azo dye. Their synthetics and application. First, methyl orange synthesis. It is prepared by coupling diazide sulfoanylic acid with N and dimethyl aniline. There is a mechanism given in application. It dyes wool and silk and impart orange color to them, but the color is not fast to light or washing. Second, it is implied as an indicator in acid-base titration. It gives yellow color in alkyl solution and pink in acid solution. The change in color at the end point is due to the change in structure of the ion. B. Congo red synthesis. It is prepared by coupling tetraazotized benzidine and with 2 molecules of naphthalene 4-sulfonic acid. Applications. It is dark red dye. It is red in alkaline solution but blue in acid solution. It is direct dye applied for dyeing cotton. The change in color from red to blue in acid solution is due to the following structural change. Fourth, triphenyl methane dye. These dye are obtained by introducing NH2 and R2 or OH group into the ring of triphenyl methane. The compounds obtained are colorless, the leuco compounds, and these on oxidation get converted into tertiary alcohol. They readily change from colorless benzoid form to quinoid dye. In the presence of acid due to salt formation, these changes are reversible. Some important dye of these class are A. Malchant green. It is obtained by first condensation of benzaldehyde and dimethyl aniline in the presence of concentrated H2SO4 to get leucobase. Second, the leucobase is oxidized with lead dioxide and HCl to color base, which is turn react with more hydrochloric acid to get malchant green. Application. With this dye, cotton is first reacted with tannin, while wool and silk can be dyed directly. B. Para-rosaline. It is prepared by the oxidation of mixture of aniline and para-toluidine with nitrobenzene. Application. Wool and silk can be dyed directly with it, producing a violet red color, while cotton is first put to dormating. C. Rose aniline, magenta or fuchsin. It is orthomethyl derivative of para-rose-aniline. It is prepared by the oxidation of an equimolar mixture of aniline, ortho and para-toluidine with nitrobenzene in the presence of iron film. The crystal of this dye show a green metallic luster. It gives deep red color in water solution. The solution is decolorized with SO2 to give Gibbs reagent. The pink color of this reagent can be restored with aldehyde. It can dye wool, silk directly and impart a violet red color. D. Crystal volatile synthesis. It is prepared by heating methylater ketone with dimethyl aniline in presence of carbonyl chloride. Application. It imparts deep violet color. Cotton is moderate before dyeing, while wool and silk can dye directly. Third, in acidic solution, it forms green coloration, which in more strongly acidic solution give yellow color. The structure change can be explained below. Application. It imparts deep violet color. Cotton is moderated before dyeing, while wool and silk can dye directly. Fifth, phthalene dye. These are dye which contain phthalene group as a structural unit. A. Phenolphthalein synthesis. It is prepared by heating a mixture of phthalic anhydride and phenol with a little concentrated H2SO4. Application. First, it is a white crystalline solid. Second, it is insoluble in water but dissolved in alcohol. Third, in alkaline medium, it gives pink color which disappears on addition of acid. The change in color is due to structure in the change in its structures. Fourth, phenolphthalein can also be used as a laxative. B. Fluorescence synthesis. It is prepared by heating a phthalic anhydride with resinols with concentrated H2SO4. Application. It is a red powder insoluble in water. Second, it dissolves in alkaline to give a reddish brown solution. Third, on dilution, the color solution gives a strong yellowish green fluorescence. The sodium salt of this dye is called uranine. Uranine dye wool, silk, yellow in acid bath. It is used for dyeing silk and wool. 6. Natural dye. Attempts have been made for time to time. Tea extract dye from plants. Dyes obtained from plants are called natural dyes. Example: a natural dye are indigo, a blue dye, and second, algerine, a red dye. It may be noted that natural dye has only limited shade. A. Algerine 1,2-dihydroxy anthraquinone. Generally, it belongs to an anthraquinone group and is one of the most important mordant dye. It is present in the madder root as a glycoside. Ribotheric acid, which on acidify or enzymatic hydrolysis yield algerine, glucose, and xylone. Structure of algerine. First, molecular formula. Its molecular formula is found to be C14H8O4. Second, distillation with zinc dust. When it is subjected to zinc dust distillation, it forms anthracene. This reaction shows the presence of anthracene molecule in algerine. Third, algerine forms anthraquinone. When anthraquinone is treated with calculated quantity of bromine, we get dibromoanthraquinone. This product is fused with KOH yield algerine. Clearly, algerine is dihydroxy derivative of anthraquinone. To support the presence of 2-hydroxy group, it is found that first, algerine on acetylation with acetic anhydride yield a diacetyl derivative. Second, algerine is soluble in water while anthracene is not. Fourth, position of hydroxyl group. A. When algerine is subjected to Vargas oxidation, it yields phthalic anhydride. This reaction proves that both the OH group are on the same ring. If it were not on, then hydroxyphthalic acid would have been obtained. A. As algerine can be synthesized by the condensation of phthalic anhydride and cation, we say that the 2-hydroxy group must be in the ortho position with respect to each other. The structure of algerine is either 1 or 2. Fifth, extract position of OH group. When algerine is oxidized with MnO2 and H2SO4, we get purpurine. Clearly, algerine is 1,2-dihydroxyanthraquinone, as this compound on oxidation yield puripurine. Puripurine was found to be 1,2,4-trihydroxyanthraquinone by its synthesis. Structure second cannot be explained the formation of puripurine on oxidation. Hence, structure second for algerine is ruled out. 6. Further support to structure first. Algerine on nitration or on acetylation produce two isomer mononitrate or monoacetyl derivative. This is only possible for structure 1. Structure second yield only one isomer. Structure of algerine. The structure of algerine is further confirmed by synthesis. Preparation of algerine. First, for madder root. On hydrolysis, the glucoside present on it break to yield glucose and algerine. Second, synthesis. It is the synthesis by starting from anthraquinone. Anthraquinone is treated with oleum at 160 degrees Celsius. The sodium salt of the product formed is fused with sodium hydroxide containing a calculated quantity of potassium chlorate at 90 to 100 degrees Celsius under pressure. Property. Physical. The ruby red crystal of algerine melt at 190 degrees Celsius. It is insoluble in water but slightly dissolved in alcohol. It sublimine on heating. It is soluble in alkaline. B. Chemical properties. First, oxidation when heated with MnO2 with sulfuric acid, it gives puripurine, such that 1,2,4-trihydroxyanthraquinone. Reduction. On reduction with zinc and ammonia, it forms anthrarobin, dihydroxyanthanol. Third, mordant dye. It is a mordant dye with aluminium. It forms red lake. Chromium give brown violet, while ferric salt forms violet black lake. They are employed for dyeing wool. Use. It is an important mordant dye. The color varies with metal used for moderating, such that red color with aluminium, violet color with black, violet black with ferrous, and brown violet with chromium. It is used as a purgative. Indigo from natural sources. The plant containing indigo is cut just before flowering and treated with water at room temperature in a wooden tank. The enzyme present in the leaves of the plant hydrolyzes the glucoside indican into indooxyl and glucose. The liquid extract is agitated in the presence of a lime in open vat when indoxyl is oxidized in indigotine, which consists of insoluble blue flakes. The curd indigotine so obtained is boiled with water. It is then filtered and dried to get indigo dye. Heyman commercial synthesis of indigo. Starting from anthracene acid, the synthesis of indigo is described below. Compared to natural indigo, the synthetic one is more cheaper. Properties. It a dark blue powder. It melts at 390 degrees Celsius. It is insoluble in water and many organic solvent. With sodium hyposulfite in alkyl medium, it gets reduced to water-soluble glyco compound called indigotine white. Its blue color is regenerate when exposed to air. Application. It is used in dyeing cotton. Its color is stable to light washing, etc. Edible dye. Food coloring or color additive is any dye, pigment or substance that impart color when it is added to food or drink. They come in many forms, consist of liquid, powder, gel and paste. It is important to note that all food has colors. Thus, colors are automatically induced which we eat different foods. It is said that rainbow eating can be beneficial. Thus, we should include food in our diet that corresponding to different color of a rainbow. At present, color additive may be harmful or not. It depends upon quantity of a color used. It is recommended that not only the use of synthetic color but the use of a natural pigment as food activities may be restricted. Different food color in a diet and their color are described below. Red tomato, beetroot, red pepper. Blue blueberry, blue stag, blue fish. Pink reddish, pink grapefruit. Yellow banana, lemon. Green pear, spinach, green pepper, leaf greens, purple, purple leaf, lecture, black grapes, etc. Thank you. This chapter is complete.